and we'll get rolling with our new material. So this week we are moving on, still talking about probability distributions, but we're going to talk about continuous probability distributions. Last week was the discrete distributions, and we focused a lot on the binomial distribution. I think that continuous distributions are simpler than discrete distributions, simply for the fact that in a discrete distribution, there are a finite number of possible values for x. So that means probability that x equals a given number can be greater than 1. So we'll say greater than or equal, or not greater than 1, greater than 0, greater than or equal to 0. If it's equal to 0, it means it's impossible, but if it's greater than 0, it has a possibility. Well, when we are looking at continuous distributions, because there's an infinite number of possible values of x, the probability that x equals a specific value has to be 0. Because if it's greater than 0, because there's an infinite number of those values, it would add up to something larger than 1. It would add up to actually something infinitely large. No matter how small a value is, if there's an infinite number of them, it's infinitely large. So each of those individual values has to have a probability of 0. Because of that, the consequence is the probability of x being less than or equal to a value is the same as the probability that x is strictly less than that value. Because the probability of being equal to is always going to be 0. And this drastically simplifies our calculations when we're dealing with continuous probability distributions. So let's do some examples of a continuous probability distribution. So the first one I'm going to do is going to look like this. It's just going to be a graph. It's going to be a triangular distribution. Now, any probability distribution has to have a total probability of 1. So that means in dealing with a continuous distribution, the probability is the area under the graph. So that means the area of this triangle has to equal 1. So if I tell you that the length here, that this top value here is 10, that would mean that this height here has to be 0.2. Because remember, area of a triangle is equal to 1/2 times the base times the height. So the base of 10 times the height of 0.2 would be 2, and then 1/2 of that would be 1. So and typically this happens a lot where we're given this distance, whether it's in a triangular distribution or a rectangular distribution, and we have to find out this height here. And the way we do that is we know that that total area has to equal 1. So anyway, let's find the probability, assuming this is a linear top piece here, and this is a true triangle. If I want to find the probability that x is between 2 and 4. So what I have to do here, I'll get this out of the way. Is I have to find the height of this at 2 and the height of it at 4. So that I can find the area. I know that this distance across here, from here to here, I know that's 2 because that's just the difference between 2 and 4. So I know that size. I know the distance between those. I just need to know those two lengths. And one of two things can happen. Either I know that this is just a triangle and I can use a ratio, Or I might be able to create an equation for this. Y equals 0.2 minus, what is that? Goes down by 0.02x. Again, for x less than 10, or between 0 and 10, I suppose I should say. So either way, let's look at the height here. If it's at 2, 0.02 times 2 would be 0.04. Oops. So 0.2 minus 0.02 times 2. Well, that's 0.04. So 0.2 minus 0.04, that's 0.16 is that height. So we get this right here is 0.16. At 4, it's 0.2 minus 0.02 times 4, which is 0.12 is what we get there. So this height is 0.12. This is a trapezoid. So the area of a trapezoid is equal to 1/2 times the larger base, 0.16, plus the smaller base, 0.12, times the distance between the bases, which we found on bottom to be 2. So that is that, 0.28, 0.14. So that calculates out to be 0.28. So the probability that x is between 2 and 4 here is 0.28, because that's just the area of that triangle. Now there's a lot of messing around there because we were simply just given the triangle its dimensions. We had to figure out this equation. And that's just going back to our basic algebra of using the y-intercept and then finding the slope of the line. Or we could have used geometry of triangles, but to me, finding the equation is way easier because you just plug in the numbers and you can find the values at that point. We're not going to do a lot of that, but there might be an example of that something similar to that popping up in the homework. Another example that might come up would just be a curve that's given something like this. And let's say we tell you that this is 3. And let's go 7 here. And I tell you that this probability here is 0.12. This probability over here, let's go 0.38. And if I want to find the probabilities, let's say the probability that x is less than or equal to 7, or just less than 7. Well, that's the complement of x being greater than 7. So that's just going to be 1 minus the probability that x is greater than 7. Notice here, I did not have to worry about is x greater than 7 or is it greater than or equal to 7? Because remember, being equal to 7 has no probability. If this were discrete like we were doing last week, we would have to worry about that. But for continuous, we do not. So this is simply going to be 1 minus the 0.38, giving us a 0.62 probability. Or if I want the probability that x is between 3 and 7, well, I have the areas outside of that probability right here of 0.2, 0.12, and 0.38. So what's in between here is just what's left over. So it's 1 minus the 0.12 and the 0.38, which actually comes out to 0.5. So continuous probability models are area models. You're finding area under the curve. Whether it is a simple curve that we know how to find areas of, like a triangle where it just becomes triangles and trapezoids, or a more complex curve like this where we have to be given some knowledge of those shapes and areas that are involved in it. But we're going to move on to, just like last week, we moved into the binomial distribution for a common distribution. Excuse me. This week, we're moving into the normal distribution. And we're going to start off with something called the standard normal distribution. remember that the normal distribution is just a distribution that follows the bell curve. Now we've seen that there are two traits that describe it: the center, the location of the middle of the curve, and then the spread, how wide the curve is, how spread out it is. For a standard normal distribution, the center of that curve is at 0. So in other words, the mean equals 0 of that distribution. And the spread is set such that the standard deviation is equal to 1. So the value is actually the number of standard deviations we are away from the mean. So if I want to find, and of course the empirical rule actually comes from this, z-scores come from this. Our values here, because of the mean being 0 and the standard deviation of 1, the values that we get here for the values of z are z-scores. So when we're looking at probabilities, we're actually going to probability that z, we're not going to use x in for this part, the probability that z takes on a certain value. Let's say probability that z is less than 1.37. So what that would mean is we would have to go up here, find 1.37, and we would find the area under that curve to the left side, or less than that. Well, there's two ways we can do that. There is a normal probability table in your book. It's well, in the ebook. It used to be a fold out when we had a hard copy book, but it's also linked in ALEKS for you to view. Or I think the easiest way to do this is to use the graphing calculator. The TI-84 does a marvelous job with this. Now, I just have a regular TI-84 Silver edition. If you have a CE, you actually have other options with this. I'm just going to go second distribution and normal. For the normal probability, we always use normal CDF. We will never use normal PDF. So I'll repeat that. We always use normal CDF. Now, this is set, so we can't say less than or greater than. The normal probability is entered as a lower limit and an upper limit. So let's go back here and think of how can we enter the probability of being less than something as having a lower and upper limit. Well, the way we do that is we enter the probability of being less than something as going from negative infinity up to that value. So we're going from negative infinity up to 1.37. The calculator recognizes negative infinity in one of two ways. I think the simplest way is just to do negative followed by 6 nines. A few more keystrokes, but it's less errors are made that way. Or we can do negative EE 99. And I'll show you how to do the EE as well. So back to the calculator. So our lower limit is going to be negative infinity. Now they've got the negative EE in there. I'll show you how you enter that. First of all, for the negative, you got to make sure you use this negative key down here, not the subtraction. The negative key down here, the negative in parentheses, and it's 1. Now, EE is not the letter E. It is scientific notation. You see here above the comma, there's a EE. That's what we want. So second, EE. That means engineering expression or scientific expression. You're going to put 99 in there. That is negative infinity. The upper bound is 1.37. Now notice it automatically puts in a mean of 0 and a standard deviation of 1. Unless you tell it otherwise, the calculator assumes we're dealing with a standard normal distribution. So we get paste and equals, we get 0.9147. We'll round to 4 decimal places here again, just like we did last week. Well, what about the other way I said that we could enter negative infinity? Let's do that. Second distribution, option 2 is normal CDF. So instead of doing the negative 1 EE99, we could have just done negative followed by 6 nines. To me, that's the easier way of doing it because you don't have to go through the scientific notation. People tend to make less mistakes there. People have problems getting the scientific notation entered correctly. So, and notice we get the exact same probability, 0.9147. Let's say we have a probability that Z is greater than 0.82. Well, again, we have to write this as a range. This is saying what's the probability that Z is between 0.82 and positive infinity. Well, you can probably guess how we enter positive infinity. It's going to be exactly how we entered negative infinity, but without the negative. So second distribution, normal CDF. Now we're going from 0.82 to positive infinity. So we either just do a 1, second, EE, 99, or we could have just did 6 9s across there. Again, mean is 0, standard deviation is 1. We hit enter, and hit enter again. We get 0.2061. And of course, then the next option is the probability of being between values. Probability from negative 1.23 is less than Z is less than 0.91. Well, this was pretty simple. This is already arranged, so we don't have anything to adjust to enter it in the calculator. So let's just go ahead and do it. Second distribution, normal CDF. We're going from a negative 1.23 to a positive 0.91. Again, mean is 0, standard deviation of 1. 0.7092. So those are the easy problems to deal with. That's just using the normal CDF command. If we want to do a reverse calculation, if we know a probability and want to find the value of Z that is linked to it. Well, there's a command. It's called inverse normal on the calculator. And what it finds is the probability of Z being less than a given value. So what we find actually is reword that. It finds the value of A such that the probability that Z is less than A equals the given value. That's a better way of putting it. So what do I mean? Let's say I want to know if find A such that probability that X is less than A equals 0.2. So what that's saying is, on my bell curve, this probability here is 0.2. Find the value of A here that corresponds to that. Well, that's simple enough. That's just going to be second distribution, option 3, inverse normal. 0.2 is the area to the left. Now, if you have the CE calculator, you actually have a option down here to choose area to the left or area to the right. Everything we're going to do, because most people don't have the CE calculator, is going to be on the area to the left setting. You just leave it there. If you want to play around with the area to the right setting, go ahead. But most of the calculators that don't have that option, these are all calculating the area to the left. And of course, our mean is still 0, standard deviation of 2. We paste and we get negative 0.8416, negative 0.84, we're going to call that. So what that is saying is A equals negative 0.84. So it's saying is this value down here is a negative 0.84. And that makes sense because if it was the center of the curve, the probability to the left would have to be 0.5. And that center would be at 0. So if the probability of being to the left is less than 0.5, we have to have a negative value of Z. If it's more than 0.5, it'd be a positive value. Well, again, that command directly utilizes the probability of being less than that value. What if we want to find the value A such that the probability of Z being greater than A equals 0.4? Well, if we look at our bell curve, what that's saying is if somewhere in here, this probability over here is 0.4. Well, what we need to use is our complements. If the probability on the right is 0.4, probability on the left is 0.6. So this A value that is going to fit this is also going to fit probability that Z is less than A equals 0.6. So that's the one we're going to solve since that's in the less than form. We'll go to our calculator. Second distribution, inverse normal, we're less than 0.6. So again, the probability of being less than A is equal to 0.6 is the same as the probability of being greater than A is equal to 0.4. And we get 0.25 is that value for Z or for A. We might ask to find the 45th percentile. This is just an inverse calculation. Remember, the percentile is the percent that's smaller. So literally the 45th percentile is saying to the left, we got 45% or a probability of 0.45. This is a very simple inverse normal calculation. We're just going to go to the calculator. Second distribution, inverse normal, and just put in that percentile, 0.45, keeping our mean of 0, standard deviation of 1. So it's a negative 0.13 would be that value. So the 45th percentile is a negative 0.13. Now remember, the 50th percentile would be 0. That would be the very center of the curve again. Let's go on now. Half of that would be 50% or 0.5. And the center of that curve is at 0. The mean is 0. Next, we want to find the values of the value A such that there's two ways we can put this. I'll put negative A less than Z is less than positive A is equal to 0.6. Or another way this might be worded is such that the middle 60% of the data is between those values. All this is saying is, we're looking at our bell curve, and we're finding taking out of the center, so there's 60% in the center. Well, there's 60% between those values. That means there's 40% outside of those values, and half of it gets split each way. So that's going to be 20% here and 20% here. So this value, this cutoff here, has a probability to the left of 20%. This value here has a probability to the left of 80%. So we're just going to look up those two values. So second distribution, inverse normal, 0.2 or 20%. Negative 0.84. Second distribution, inverse normal, 0.8 or 80%. And you'll notice we have the exact same number, only positive. And since it is the center of the curve, it makes sense. The center is at 0, so the left side and the right side are the same distance away. So they're the same number, just one's negative and one's positive. This is a negative 0.84. This is a positive 0.84. Well, that is the standard normal. curve. Let's look at a general normal distribution, or what's sometimes called a, flip my page here, a generic normal distribution. In a general normal distribution, the mean can be anything and the standard deviation can be anything. So for our example here, let's look at the mean, mu of 20, and the standard deviation of 5. So let's find. Notice I'm not using z now for my variable. It's now x because it's not a standardized distribution anymore. So we're not looking at z-scores. We are looking at just pure x values. Let's find the probability that x is less than 15. Well, this is just going to be a simple calculation that we got to turn into a range from negative infinity, less than x, to 15. So let's go ahead and punch that in. So second distribution, normal CDF from negative infinity. I'm just going to use the negative followed by 6 nines. That's just way easier for me to enter. I know it was already there, but that's okay. Up to 15. But now we do have to change the mean. The mean here we said was 20, and the standard deviation is 5, giving us 0.1587. So this probability of being less than 15 is 0.1587. We might have the probability x is greater than 30. Again, this has to be turned into a range. This is probably 30 is less than x, which is less than a positive infinity. So let's enter that in. So second distribution, normal CDF, we are going from 30 as our lower limit up to positive infinity. Again, I'm just going to enter 6 nines for that. Mean is still 20, standard deviation is still 1 or still 5. Hit enter and enter. 0.0228 is that probability. Next, we want to find the probability that x is between 10 and 25. Well, this is already a range, so you just go ahead and enter it just like that. Second distribution, normal CDX, going from 10 to 25, with a mean of 20 and a standard deviation of 5, giving us 0.8186 is that probability. Have initial loading here, just a second. Hopefully it'll catch up in just a minute. There, hopefully that's better. So this will just be a normal CDF from 10 to 25 for this. Second distribution, normal CDF, 10 to 25. So that's already that stayed in there. Let's just go ahead and hit enter and enter again. You get 0.8186. Is that probability? Okay, so now let's do those reverse calculations again, like we did with the standard normal distribution. Find the probability, or find A such that the probability that X is less than A equals 0.3. So this is going to be an inverse normal. It's less than, so it's what the function is made for. So second distribution, inverse normal. Area to the left is 0.3. Our mean, however, has to be changed to 20, and our standard deviation is 5. Now we hit enter and enter again. We get 17.38. So A equals 17.38. What does that mean? Well, again, that's going back to our curve. The probability to the left here of 0.3, it's saying this value is 17.38. It makes sense because the center would be 20 because that would be the mean. So 0.3 is off to the left of that. So 17.38 makes sense. Find B such that the probability that X is greater than B equals 0.1. So what we're looking at here, probably out here, so that this is just 0.1, and we want to find this value of B. Well, again, that's to the right, and most of our calculators only do the area to the left. Well, if the area to the right is 0.1, the area to the left would be 1 minus 0.1, or 0.9. So that's what we're going to be looking up here. So we go to the calculator, second distribution, inverse normal. 0.9 is the area to the left for a mean of 20 and standard deviation of 5. Giving us 26.41 is that value. So this B here is 26.41. You see something in the chat quick. That's a very good question. These, because the peak is so much higher, it's not quite that easy. Like here, we know that, so this, since this probability is 0.9, we know that the value is going to be way off over here. So this better not be real close to the mean. The mean would be 20 in the middle. 26 is quite a ways away from the mean. It's more than a standard deviation away. So that makes sense that it would be further away from the mean. Whereas this one of 0.3, that's closer to the middle. So this should be a little bit closer to our mean of 20. So yeah, you can sort of use that to double check, but the probabilities in the middle get large very quickly. Like if I wanted to find, the probability of being between 15 and 25, that's just one standard deviation on each side. That's going to be over 0.68. I think it's 0.6844. That's pretty large. So we have to be very careful to think, okay, if probability of X being less than 15, is it already down to 0.1587? So even though 15 is only one standard deviation away, the probability of being smaller than that is a fairly small probability. Let's look at find the values such that the middle 80% of the data is between them. So this, once again, we're looking at this bell curve and we're looking for 80% out of the middle here. Well, if 80% is out of the middle, that means there's 20% to the outside. And since it's symmetrical, that's split 10% on each side. So 10% there and 10% here. So that means that we have this cutoff here that has 10% to the left, and this cutoff here that has 90%, 10 plus 80 to the left. So we need to do the inverse normal for 10% and the inverse normal for the 90%. So let's find those two probabilities and we'll plug them in here. Second distribution, inverse normal, 0.1, mean of 20, standard deviation of 5 yet. Giving us 13.59. I'm going to go ahead and write that one down so I don't forget. So this end here is 13.59. And the other end, the 90%, second distribution, inverse normal 0.9, mean of 20, standard deviation of 5. 26.41. Now this one, there is a little bit more you can check. These two numbers should be the exact same distance away from the mean. Remember, the mean was 20. Both of those are 6.41 away from the mean. So it's true that the middle 80% of the data is between 13.59 and 26.41. Okay, let me get to the chat here again. $40 instead of 20 for what?
Above 80, because I thought put the 20s on both ends because it's half of the 80%, but yeah.
No, it's not half of the 80%. It's 80% in the middle. So the 20 here is 100 minus 80. Gives us 20 that's left over.
Oh, shoot. Okay. Thank you.
Then that 20 has to be split to each side. So that's 10% on each side.
Okay. I missed that.
Sure. Yeah, remember that whole bell curve has to add up to 1 or 100% if you're thinking of it in percents. So now the next step is something called a sampling distribution. A sampling distribution is a very important application that bridges this normal distribution into our inferential statistics that we're going to be doing the next 4 or 5 weeks. And what it talks about is if we have a population with mean, I'm just using capital U, and standard deviation of capital S. If we take samples from that population, of size n, if we find the mean of each of those samples, those sample means are now the elements of our sampling distribution. So what's in this distribution is not the individual values, it's the means of all the possible samples of size n. The mean of those sample means should equal U, the population mean. The standard deviation of those sample means, often referred to as the standard error of the means, should be equal to S, the standard deviation of the population, divided by the square root of the sample size. The bigger the sample is, the less variation there will be in the sample means. So let me repeat that. The larger the sample is, the less the sample means will vary. The smaller the sample is, the more they will vary. If you think about it, it makes sense, because if I'm looking at the bell curve here, here's my individual values. If I'm taking a sample of just 4 items, well, if I randomly select an item with a really small value, chances are at some point I'm going to select an item with a larger value. And when I find the mean of that sample, those are going to cancel out and give me a mean closer to the middle of that distribution. So it makes sense that there's less variation the bigger the sample is. Even with just a sample size of 4, I mean, it's possible that we could get all 4 really small numbers, but chances are we're going to get some couple of small ones and a couple of large ones, and they'll still average out to be close to the middle. So let me show you what we mean by that. So let's say the population has a mean of 72, standard deviation of 9. Let's find the probability that a randomly selected student has a score of more than 80. So this is just a single value. This is the probability that X is greater than 80. So we're just going to do a normal CDF of being greater than 80. So second distribution, normal CDF from 80 to positive infinity for a mean of 72. And this is a single per student, an individual value. So it is just the standard deviation of 9 here, giving us 0.1870 is that probability. So again, that was just a normal CDF from 80 to infinity for a mean of 72 and a standard deviation of 9. But my next example, my next question is going to be to find the probability that the mean of a randomly selected sample of 12 students is more than 80. So now we have 12 students that we've randomly selected, and we're finding the mean of their test scores. We want to see if that value is more than 80. This is not the probability that X is greater than 80. This is the probability that X bar, the sample mean, is greater than 80. Well, this is a sampling distribution because we're trying to find the probability of the mean of a sample being a certain value. So this is not going to be just normal CDF anymore. We are using the normal CDF function. We're going from 80 to infinity still. Our mean does not change, it's still 72, but what changes is instead of the standard deviation of the population, we have to use the standard deviation or the standard error of the sample means. And that is always equal to the population standard deviation, which is 9, divided by the square root of the sample size here, which is 12. And we can actually enter it right in the calculator just like that. So go to the TI-84, second distribution, normal CDF. We're going from 80 to infinity, so that doesn't change. Our mean is still 72, but we replace the standard deviation with the standard error of the mean. So it's 9 divided by second square root of 12. Close those parentheses. And there we go. We get a 0.0010 for that probability. Now you think about it, that does still make sense because we're looking at our bell curve. The center of it is 72. 80 is up here. Probability of a single value being greater than 80, yeah, right around 18.7%. That sounds pretty good. But for the mean of a sample to be up there, remember, when we do a sample mean, basically what's happening is the curve is getting narrower because we expect the means of the samples to be closer to it. The standard error of that is the population standard deviation of 9 divided by the square root of our sample size, the square root of 12. That calculates out to be 9 divided by the square root of 12. Oops, I don't need that. Gives us 2.60598 we'll go, 2.598. That's the standard deviation now, or standard error, instead of the 9 that we were using before. So now that 80 is several standard deviations away from the mean because we're looking at the means of the samples rather than just single individual values. So when we're talking about sampling distributions, that's something you have to keep in mind. So again, population mean 72, standard deviation of 9. Find the probability a student will have a score less than 70. A sample of 18 students will have a mean score less than 70. So again, this one up here is just a student. That's an individual value. So that's just going to be our regular calculation. This is just a regular distribution. Normal CDF, we're going from negative infinity because we're less than up to 70 for a mean of 72, standard deviation of 9. Down here, however, this is the mean of a sample of students, a mean of a sample of 18. So this is a sampling distribution. So we're still going from negative infinity up to 70. We still have a mean of 72. The mean of our sample means, the mean of our sampling distribution is always equal to the mean of the population. It's the standard deviation that has to be adjusted. So it'll be 9 divided by the square root of our sample size. So the sample size here is 18. So it's 9 divided by square root of 18. So let's find this value here for the single student. Second distribution, normal CDF, going from negative infinity to 70 for a mean of 72, standard deviation of 9. We get 0.4121. So about 41% chance that a student will score that low. Now for this group of 18 students, we're expecting, since we're going, well, this is away from the mean, we're expecting it to be a significantly lower probability again. So second distribution, normal CDF, still going from negative infinity to 70. Mean is 72. It's now the standard deviation has to become a standard error. So 9 divided by the square root of 18 students. We get 0.1729, which is exactly what we expected. Significantly smaller probability. So you have to be very careful when you're doing these probabilities to look, are we looking at an individual? So we're just going to use normal probability? Or are we looking for the mean of a sample? So that we would have to be using the sampling distribution. And the difference is when we enter it, if it's the mean of a sample, we have to adjust that standard deviation to turn it into a standard error of the means. That is all we have for you this week. This left you with the big one here, figuring out probability distributions versus sampling distributions. That one's going to be tough. the 18, because this was a sample of 18 students here, so that's why we had to have the square root of 18. It's the
Oh.
square root of the sample size.
Thank you.
You bet. Any other questions?
Is there a way to remember to square root that? Just be mindful of the sample size.
Just the fact
Right.
that it is the mean of a sample that we are looking for rather than just the value of an individual is when you
Okay.
need to know you have to divide by that square root of the sample size.
Okay, thank you.
That's going to be one of the trickier ones to figure out as we go through this week.
Yeah.